Hi, everyone. I'm recording a quick supplement for the solution to assignment 3, which is posted on the website. So we'll get right into it. The first question basically asks about those two rat breathing patterns, which are periodic. That's important to recognize. And we have basically two autocorrelation functions of those to interpret. And I think most people actually understand what's going on here. You have to think a little bit about how you calculate an autocovariance function and how that would play with a periodic signal. Okay, and so there's an explanation here, but the fact that the autocovariances oscillate indicate an oscillation in the signal, right? Because if you think about the shift and add procedure, shift, multiply, and add procedure, when we shift over by a full period of the periodic function, then it's going to be back in phase again, and we're going to get a strong positive correlation, right? And then if we shift over by 2 periods, then they're back in phase again probably, and we get a strong positive correlation. And that's actually going to alternate with negative correlations when they're like 90 degrees out of phase. I can show you an example in MATLAB, actually. Okay, so basically, if I make a perfectly periodic signal, a sinusoid, right? It's a cosine function. And then I compute its autocovariance. Notice that I'm using the unbiased option with the XCOV function. And then I plot the result. This is what we get at lag of 0. They are perfectly aligned with, the function is perfectly aligned with itself, of course. And then as you shift, along the lag axis relative to the other, when you come around and shift a full period, then they are perfectly aligned with each other. And you go 2 periods and 3 periods, then the sinusoid's back in phase, right? And so if you have a perfectly periodic signal, this will continue on forever to any number of lags, because you just, as you shift for one full period or any integer number of full periods of the sinusoid, then the two versions are perfectly in line with each other, and they're going to give us a strong positive correlation, which is going to, again, alternate with, relatively strong negative correlations when they are, 180 degrees out of phase with each other, right? One of them will be positive, the other one will be negative, and so on. Okay, so this is sort of what's happening with these rat breathing patterns. The main thing that's going on, though, is that this starts to drop off, right, as you get away from 0. And the whole point there is that this is not a perfectly periodic signal. And so what, if the autocorrelation drops off after a few cycles, then what's happening is there's been some change in the periodicity of that. Either the waveform has changed a lot, or more likely the period of breathing has changed. And so as you kind of shift several periods of the oscillation away, then the waveforms don't line up so well anymore, and we start seeing that dropping off. And so in the case of, a rat where that breathing pattern remains consistent for a longer period of time, then it's going to look like something closer to this ideal case, but it'll still drop off, right? Because this is, real data that comes from a real subject, presumably. And so it's not going to be perfectly periodic. The waveforms are going to vary a bit. But if it's consistent and the rate of breathing is consistent, we're still going to retain high covariances for several periods. Whereas in the second rat case, this drops off much faster, which is probably an indication that the period of breathing, the rate of breathing, is changing and may be kind of variable. Okay, so those, even after a few breaths, those waveforms don't line up very well anymore. And so there's a lot more variability in the breathing. And so the most likely interpretation really is that the breathing period is less regular and tends to vary more. Most people made that observation, so that's actually good, but you know, it's worth, if you can reason through that and make that all make sense to you. Okay, for number two, basically I kind of preferred that you kind of do a manual or semi-manual calculation of the covariance here by using the shift, multiply, and add technique, just to get an idea of the mechanics of that, because this is what MATLAB does, mostly, sort of, okay? But in interpreting MATLAB's results, it helps to really understand how this approach works. Okay, and so of course the idea is we want covariance, so you can actually subtract off the mean at the beginning, or you can subtract off the mean squared at the end. Either way, you should get the same answer. I subtract the mean at the beginning and then have a new, you know, a modified signal with the mean of 0. And then I line them up, I multiply each case, I sum those, and then I average those. And it's important to think about that as the average. So here I have 10 examples and I divide by 10. When I shift by 1 and do the same thing, right, I only have 9 examples now. So I have to divide by 9. Lag 2, 8 examples. So I divide, and when averaging, I'm dividing that sum by 8. Okay, and so I get these numbers for the 0, 1, and 2 lags. Okay, now if you, and that says something about, you know, how quickly does it, within maybe 2 time samples, it kind of has a tendency to shift to the other side of the mean. That's more or less what we're saying here. And again, this is a pretty short signal, so the conclusions are kind of iffy, but yeah, you start here with it after 2 time points, it's on the other side of the mean. Here, maybe not so much. Here, definitely. Here, definitely, and so on. So it has a tendency to do that. That's how we might interpret that. Within 1, it generally tends to be on the same side of the mean. That's kind of, and again, not always, but on average for the most part. One thing I want to note is, okay, if you do that with that data, so I have plugged this data into MATLAB and you just do XCOV directly on that data, you're going to get some different numbers, okay? 4.42, this is 0 lag, 2.29, etc. Those are not scaled at all. They didn't divide by 10 or 9 or 8 at all. And that's MATLAB's default behavior, which I completely disagree with, okay? To get something that matches my data, you have to use the unbiased option, okay? And if you do that, then you will get 0 lag 0.442, lag 1 0.255, lag 2 minus 0.0595, which agrees with what I have. Okay, so the unbiased option in MATLAB does it the way that I prescribe, okay, and matches my data. So be aware of that. If you know, in any other cases where we're taking covariances, correlations, cross covariances, cross correlations, choose the unbiased option, okay? And your results will make more sense, okay? All right. Part 3 was basically working with expected values and kind of working through some things. And in general, this is done okay. I would say the places where people make mistakes tend to be, say, here. Okay, so first of all, you know, F is the sum of two processes, and then we work through the linearity of the expected value. We get 4 terms, right? This is RXX by definition, which we did not know any more information about. So that's as simple as we can get. And we cannot break this into E of X times E of X of t plus tau because they depend on each other. I mean, X is dependent on itself, okay? We get the cross terms, which we'll talk about in a second, and we get R and N for the 4th term. The cross terms, notice, can be broken up because N and X are independent of each other. And that's the only reason we can do that. But a mistake a lot of people make is plugging in 0 here. But N is not 0 mean, okay? The mean of N is actually B, and the mean of X is actually A. And so this product has a value of BA and is not 0, okay? And the other cross term is similar, would be BA as well. The 4th term being the autocorrelation of N, but because we have more information about N, we can do a little more. So if we simplify the autocorrelation of N, N was M, a white noise process, plus a constant B. So we plug that in and we get 4 terms again. This is RMM, but M is white noise. And so here's a mistake that people make. The RMM, the autocorrelation of white noise, would be its variance times a delta function. A lot of people leave out the delta function. The delta function has to be there because it's not just S squared, that would be a constant, right? The delta function is actually quite critical. The cross terms, of course, become 0 because the expected value of M is 0. So there are no cross terms there. And then B is a constant. So its expected value is B squared. Expected value B squared is B squared. And so the result of the 4th term becomes this. And so when you plug it all together, you get this quantity with 4 terms in it, okay? The easy way then to get the autocovariance is to subtract expected value of F quantity squared. So let's find out what that is. That's relatively straightforward, right? Because it's just a sum. We get the expected value of X and the expected value of M and the expected value of B, which all comes out to A plus B. When you square that and subtract it, you end up getting that CFF is equal to RXX plus S squared delta tau minus A squared. And it turns out that CXX is actually RXX minus A squared because the mean of X is A. And so this actually ends up being what you would expect to see. The covariance of the sum is the sum of the covariances of X and N, okay? Because the 1st and 3rd terms here are accounted for by X, and then this is accounted for as C and N, okay? So those are the results. And make note of those 2 places that I pointed out where people frequently make mistakes. Part 4 says, okay, we have a random process with an autocorrelation that is a sinc function. So what can you interpret about that? Well, we can talk about its power spectrum by taking the Fourier transform of its autocorrelation, okay? And the Fourier transform of a sinc function is a rectangular function. Some people make a mistake with that, but that's one of the ones you really have to know, okay? Sinc function, rectangular function. Even if you don't, you know, and I don't know off the top of my head the exact relationship, but sinc function, rectangular function should be in your head. And so a signal like this would be kind of positively correlated and then negatively correlated, and that kind of drops off, actually, like the example from problem 1 in some ways. And so the random process would kind of have a tendency to oscillate, is what you would expect if you take examples from that random process. The power spectrum tells us, being a rectangular function, basically says, okay, examples from this random process are going to have frequency content up to a certain point, and then nothing above that, right? And so it's going to be limited in how fast it can change. So it will tend to be oscillatory up to a certain frequency, but not really going beyond that. And those are kind of some of the things that we could interpret from both the autocorrelation and the power spectrum. Part 5. So here there were in several cases confusion between having a Gaussian autocorrelation and being a Gaussian white noise process, and those are two different things. Okay, so pay attention to what it says here. The power spectrum of a process with a Gaussian autocorrelation function by the Fourier transform is a Gaussian whose width is inverted, right? The sigma parameter is inverted. When we take the Fourier transform, that's one of the ones you should know because we use it as an example a lot. And so as you get wider in the time domain, as your autocorrelation becomes wider and you have more positive correlation over longer time periods, the Fourier transform becomes narrower, meaning it incorporates less high frequency stuff, meaning it can't change as fast, right? And so a wider kind of positive correlation field implies less high frequency stuff. Both of them imply we can't change so fast, okay? We have stronger relationships between things that are further apart in time, all right? So you can interpret it from either perspective, right? From the autocorrelation perspective or the power spectrum Fourier transform perspective, and they both should get you to the same place, okay? Part 6. So we have these two signals from two random processes. We compute autocovariance estimates. As you get to long lags, you probably don't want to rely on those. So this one, maybe out to about here, this range. This one drops positive to negative, maybe to here, maybe just to here is what we want to consider, although these negatives look fairly significant. So we probably need to keep an eye on that. Okay, and then I ask you to look at power spectra. So both the power spectrum from the signal itself, magnitude squared, or the power spectrum from the autocovariance estimate, which would be just the Fourier transform of the autocovariance estimate. And you find that they occupy similar parts of the frequency space, but a frequent misunderstanding here is getting them on the same frequency scale. So the thing to notice is, depending on how many lags you use in your autocovariance function, if you use the full range, as I did, then you actually have, this is twice as long as the original signal because it does both the positive and negative side of the full range of lags, even though it's symmetric. It's just MATLAB's behavior. Okay, so the effective recording period for the autocovariance signal is twice as long as this. Therefore, the frequency elements are scaled differently, in fact. And so what I did to kind of demonstrate that is noted the frequency units in terms of cycles per X number of samples. In the original signal, there's 512, but in the autocorrelation signal, there's twice that, or roughly twice that, 1,023, okay? And so as a result, I have scaled these to graphs accordingly in order to get it correct. Now you could also reduce these to cycles per sample because the sample interval is the same. It's just the full recording period is different, and have them on the same frequency scale. Okay. But this is a place where it's really important, and I noted this on some of the homeworks, to have your units straight in the frequency space. Okay. But we didn't really, if we knew the sample time, which we didn't in this case, we could have done cycles per second as a way of kind of unifying the two of those, and that would have been fine. Similarly, for F2, we get a similar result where they kind of look very similar. There's, there are going to be slight differences. They shouldn't be identical, but they do kind of come from the same place originally, right? They come from the same original signal. Okay, last one, sleep data. When you look at the power spectra, you see we're looking at left and right eyes, so we expect a lot of similarities here. We see that one tends to, they occupy kind of the same space. One tends to be stronger than the other. That's probably just because the transducer is less sensitive for one reason or another. And so, one side maybe is less sensitive to than the other, but they occupy roughly the same frequency space, which we would expect. Up to about roughly 0.4 hertz. Now, I asked you to look at the cross covariance, and this is an example of, okay, you got to find the right scale on which to look at the data, okay? And so sometimes people just look at a small range of lags, which give you just this little bitty part up here. Sometimes people look at the full range of lags, which makes this thing look like a delta function, and you miss the details. And so, as I'm always encouraging you to do, you really have to explore the data a bit to find the right scale on which to look at it. And in this case, the right scale to look at the data is within plus or minus a few seconds. In this case, I plotted out to plus and minus 5. Because if you look at this, right, the autocorrelation, or the cross covariance stays pretty high and drops to 0, at about plus and minus 2 seconds, okay? Cross covariance functions, by the way, do not have to be symmetric. This is slightly not symmetric, but it is close to being symmetric, at least in kind of a global sense. And so the interpretation of that is that the left eye is highly correlated with the movements of the right eye out to about plus or minus 2 seconds, and vice versa. Okay. Another way of saying it is, if I know the left, if I know something about the signal from the left eye right now, I have I have information to predict the behavior of the right eye for about up to the next 2 seconds, and vice versa. Right eye predicts left eye up to about 2 seconds. So they tend to move in a very coordinated fashion, which is exactly what you would expect the eyes to do. Okay. It turns out this looks very much like the autocovariance function for either one of the eyes, which I didn't ask you to calculate, but it will look very, very similar, in fact, because the eyes are so correlated, right? They're so well coordinated that that actually should happen, right? So this is a case where cross covariance reveals a very strong relationship, and it's certainly one we would expect if we were to just kind of think about it off the top of our heads. The eyes are synchronized, so they should move together, and this signal reveals that they do. Okay. Okay. So that's all. So again, just to repeat the point, one of the big keys to this one is looking at it on the appropriate scale in order to make those kinds of interpretations of, what is the time range over which they do have a strong relationship. Okay, that's what we can kind of derive from this data. Okay, that's going to do it for solution to A3, and we'll see you in class.